Hi, I'm Al McRobbie at Saley Company, and welcome to part 4 on our series of torque transducer videos. And we're continuing on developing some more specifications or having some more insights into our motor here that came with very little specifications. One of the things I wanted to have a look at is the starting current and the torque that can be developed when you first turn a motor on, whether it's unloaded or fully loaded or loaded to the degree that you're going to be using it in your system. And there's an interesting synergy that can occur between TorqView and an oscilloscope because of the peak hold function on the speed and torque indications, as well as well, in a digital storage oscilloscope you have peak hold because you can freeze the traces. So you can actually get a pretty good estimate of what the current actually is, and you can get a torque number from TorqView, and then you can start to use these two pieces of data together. So I'm going to just demonstrate a couple of these really quickly, and then we'll talk about some of the calculated values briefly. Okay, so what we're going to do is we're going to just make sure our loads are off, and we're going to do a starting impulse with under no load. Okay, so here goes this whole thing. I'm going to start the oscilloscope. I'm going to turn this on. You're going to watch what happens on the screen. Okay, we saw something like this similarly before. Okay, I'll turn it off, and we'll stop the display. You can see that here. Okay, so you can see right here that we got an RPM value of 783 RPM. Now over here, if you look at what's happening on the oscilloscope, we can use our cursor measurement to actually measure what the steady state current was, which is about 320 milliamps. But look at the impulse here of the starting current. I'll zip up to that and we'll take a look at how much that is. This motor drew approximately 3.2 amperes on startup. Okay, so that's an interesting thing to know. Now let's compare this when we put on full load. We'll run the more or less same test over again. Let me zero my peaks. Go back to here. All right, here we go. This is going to be our full load, which is basically half speed for this motor. Okay, so there we go. I will stop this right here, very conveniently. Now you can see that when the motor is running at its mid-speed, that it's drawing about 2.68 amperes. You can see that on the oscilloscope screen down in this area right there. There's the average point of the motor current waveform right here. So going back over to the digital part of TorqView now, we can see that we achieved a speed of 433 RPM, and we have a peak torque of roughly 344 millinewton meters. So let's talk about some of the other parameters that you can derive from this. We can talk about torque constant, speed constant, and the speed torque gradient. Torque constant is expressed as newton meters per amp, and this can be determined from the torque current graph, which you'll see on the screen shortly. That's the slope of the line. The speed constant is RPMs per volt, and the speed torque gradient is RPM per newton meter. Now, the other thing that we can do with this is we can determine amperes at torque stall by using the stall torque value determined graphically in the torque constant. The value of the stall torque current can be determined from that. This is a useful number to know if you need to design a motor protection circuit for overcurrent. So these are some of the things that we can get. From using the torque transducer and some of these other pieces of equipment, we can fairly easily fully characterize a motor. So In our next segment, I'm just going to talk a little bit about the equipment that we used and where we got it from, and special thanks to people. So thanks for watching this one too.